Welcome back to the next chapter in calculus. In this chapter, we are going to be looking at a thing called derivatives. Derivatives are a foundational piece in calculus. Derivatives and integrals form up the base, the bulk of intro calculus. For the advanced calculus, we'll also get to infinite sequences and series, but generally speaking, calculus is thought of as its derivatives and integrals. The limits that we were doing are foundational in that they form the base of the derivatives and the integrals. So first, in this first section, we're going to see what is a derivative. What does it mean? How do we find it using the definition? And then we'll find more ways and more uses and stuff in the rest of the chapter. And then even the next chapter is more on derivatives. Derivatives are a huge piece of what we're doing. So, looking at this one, we're looking at the definition of a derivative. So, what is a derivative? Derivatives have some meaning. Derivatives can be the slope of a tangent line to a curve at a given point, instantaneous rate of change, velocity or acceleration, depending on what we're talking about. But the biggest thing that derivatives are, what is a derivative? A derivative is a slope. That is huge. The derivative is a slope. We were so close to finding derivatives at the very end of chapter 1. It's ridiculous how close we were. And we're just going to pick up right from where we left off and take that one last step to take it from just the difference quotient to a derivative. And so these are definitions, it's more meanings of derivative, but that doesn't help us figure out how to find a derivative. To find a derivative, we're going to look at what's called the limit definition of a derivative. The limit definition is the derivative of function f of x is the limit as h approaches 0 of f of x plus h minus f of x over h. This was the difference quotient we were looking at the end of last chapter, except we weren't taking the limit as h went to 0. We made h, which at the time we called delta x, we made it just something really small. We used 0.01. But now we're going to make it smaller and smaller and smaller. So really, we're finding the slope as these 2 points become 1 point. And that is the derivative. It's as those 2 points get closer and closer together, that line that they're making, if you connect the dots, gets closer and closer to being an actual tangent line instead of a secant line. So that's the limit definition. We're going to use this a lot, at least today. There is another slight variation to this equation. It could also be the limit as a goes to b is f of b minus f of a over b minus a. Same idea. It's taking the slope between 2 points as those points get closer and closer and closer to each other. This one uses 2 distinct points, whereas the first one uses 1 point plus a slight difference to that point. Honestly, I use the top one almost always. The bottom one is easier if you are finding the derivative at a certain point, but even for that, I use the top one, and we'll see why later on when we do an example. So, before we get to an example though, let's look at some notation. Calculus was developed by a couple different people simultaneously in different places of the world. Well, kind of different places in the world. I mean, it was still Europe. It may have been developed elsewhere. We just don't know about it because we don't. But even in Europe, it was developed by a few people at the same time, and they used different notation. Of the people that have notation, we'll see Leibniz's notation, Lagrange's notation, Newton, because Isaac Newton developed it, and Euler. Leonhard Euler also developed it. Interesting side fact, my cat's name is Leonard, after Leonhard Euler. So anyway, but of those 4 types of notations, we really only use 2 of them. The other 2 have their uses in, I want to say, fairly obscure topics, but it's not necessarily obscure topics, but topics that we're just really not going to get to this year. So looking at the types that we'll use, Leibniz's notation, so we have a little bit of history. So the derivative is slope. It's change in y over change in x, or delta y over delta x. But since the change was so small, use a lowercase delta. The lowercase delta looks like that, which for convenience, maybe sloppiness, it just became d's. So for Leibniz's notation, the derivative is dy over dx, which we could also use if we have a function. We can go d over dx of the function. For example, if we wanted to have the derivative of the inverse sine, we could write d over dx of inverse sine of x. So it doesn't have to be just dy over dx. It could be this. This type of notation is very useful when we are dealing with partial fractions, implicit differentiation, a few more things that we will get to later on this year. It's also nice when we are like listing rules, because I could just have d over dx of sine inverse of x equals whatever it equals for its rule. We don't have to define the function first, like we will for our next type of notation. And this type of notation is Lagrange's notation. Now, funny enough, this is not even the funniest name we're going to see in the next couple weeks. But this one's also known as prime notation. I'd say, at least in the beginning, this type of notation generally tends to be more common. It's what I'll use more often, and it's easier when we're working with functions. But prime notation, if we have the derivative of function f of x, that's f prime of x. The derivative of y is y prime. And so you just pronounce the apostrophe as prime. And so this one, if we were doing the limit notation, for function f of x, f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x over h. If we wanted to define a function like the inverse sine function, we'd have to say f of x equals inverse sine x, then f prime of x equals whatever that's going to equal. And we will get to that, but not in this chapter. And so those are the types of notations we're going to use. I wanted to get that done before we do an example, because it's hard to talk about a derivative, especially as an equation, without having the notation to use with it. So let's look at how we find the derivatives using the definition. And this is what you're going to be doing in this section, by the way. So if we have a question, find the derivative of f of x equals x cubed. So to do this, we're going to use the limit definition. F prime of x will equal the limit as h goes to 0 of f of x plus h minus f of x over h. That's just the definition. Like, we haven't inserted any content there. Now we'll insert some content. F prime of x equals the limit as h goes to 0. F of x plus h is going to be x plus h cubed. X plus h cubed minus f of x is x cubed over h. So now if we just plug in 0, we're going to get x cubed minus x cubed over 0. It's 0 over 0. That doesn't do us any good. We need to distribute this x plus h cubed. So luckily, for the past couple years, you've been learning about binomial distribution, which makes that so much easier. And I know for a fact that your teachers would have told you that this is important because you are going to use it in the future and it's going to make your life so much easier, and you listened and so you understand it. And so that's going to be wonderful. I'm so happy for that. But when we expand this x plus h cubed, we're going to get x cubed plus 3x squared h plus 3xh squared plus h cubed. And then we have this minus x cubed at the end, right? That's not the binomial expansion, that's just this minus x cubed all over h. So now we can start simplifying. Looking at the top, we have some like terms. We have x cubed minus x cubed. Those will end up canceling each other out. And then what else? Like, what does all the top now have in common? They all have an h in them. So let's factor out an h. F prime of x equals the limit as h goes to 0 of h. What we have left will be 3x squared plus 3xh plus h squared all over h. The h's will now cancel, leaving us with no fraction. So now if we plug something in, we're not going to get 0 over 0. So let's plug in 0 for h. F prime of x equals the limit. No, we don't need the limit anymore. We're plugging it in. So f prime of x equals 3x squared plus 3x times 0 plus 0 squared. Well, 3x times 0 is 0. 0 squared is 0. Those go away. So we're left with f prime of x equals 3x squared. That is the derivative for x cubed. This is the process you're going to be using quite a bit. And there's really two ways. There's finding the derivative, which we just did. We end up with an equation. And there's finding the derivative at a point. And so a lot of times you actually start out with that. Use the other formula, the f of b minus f of a over b minus a, and you find that limit. And that's great. I don't start out with that. I actually start out with this because now if we wanted to find it at, say, x equals -1, we would just plug -1 in for x. -1 squared is 1 times 3 is 3. If we wanted to then find it at x equals 2, plug in 2. 2 squared is 4 times 3 is 12. We wouldn't have to go through the steps all over again. We have a function. We can plug in whatever numbers we want into that function to get the derivative at that point. And so finding the derivative at a point all on its own, yeah, it's nice, but it's not as useful. That's why we started with this. We can find the equation, and then we can plug in whatever point we want. So let's see one of those. Find the derivative of f of x equals x squared plus 2x minus 7 at x equals 2. So the same steps. F prime of x equals the limit as h goes to 0 of f of x plus h minus f of x over h. And yes, I tend to write down the equation every single time because now I can plug stuff into it. F prime of x equals the limit as h goes to 0. F of x plus h means we're going to plug x plus h into both the x's. So we'll have x plus h squared plus 2 times x plus h minus 7, and then minus the function, x squared plus 2x minus 7. X squared plus 2x minus 7. So if you look on the side of your phone, you can see the rest of that equation. The parentheses are there. If not, let me know. I'll bring my Sharpie over and I'll put the parenthesis right where it goes. So we have that, and that's all over h. We need to multiply some stuff out. F prime of x equals the limit as h goes to 0. X squared minus 8, or x squared plus h, remember, is not x squared plus h squared. Don't be that guy. It is, however, x squared plus 2xh plus h squared. We can distribute the 2 here, plus 2x plus 2h minus 7. And now distribute this negative. That's key. Minus x squared minus 2x plus 7 all over h. We can cancel what we have in common because we will be able to cancel stuff we have in common. We have an x squared minus x squared. We've got a plus 2x minus 2x. And we have a minus 7 plus 7. Those can all cancel. Everything from the f of x will always be able to cancel, leaving everything that's left has an h in it, always. With polynomials, when you get to like trig, it's a little bit funnier, but with polynomials, that is always the case. So we can factor the h out of those remaining terms. F prime of x equals the limit as h goes to 0 of h times, we still have a 2x plus h, and then plus 2 all over h. Cancel the h's. And now we can plug in 0. F prime of x equals 2x. The h will become 0 plus 2. Now we wanted to find it at x equals 2. So we just plug in f prime of 2 equals 2 times 2 plus 2. 2 times 2 is 4 plus 2 is 6. So f prime of 2 equals 6. And again, this is nice because if we have part 2 of the problem saying, all right, now find what it is at x equals 10, we just need to plug in 10. 2 times 10 is 20 plus 2 is 22. And we can get it from anywhere. So these are the two basic types of questions that you'll be doing. Yes, you'll be doing a bit of expansion. You'll be doing a bit of multiplication. That comes with the territory. But This is using the limit definition on only polynomials. I'm only throwing polynomials at you. You don't have to worry about exponential functions today, or logarithms, or trig, or anything like that. We'll get to those later. But keep working problems, keep asking questions, and until next time, happy mathing.